Bill Gates has financed a nuclear reactor in Wyoming that just started construction. It's the first of its type, and I've had a look at what's new about it. Before I talk about the new reactor, a big thank you to all our supporters on Patreon, especially those of you in Tier 4 and higher. This channel would not be possible without your help. And you too can help us. Go check out our Patreon or join us right here on YouTube. The new reactor comes from the company TerraPower, and they call it a Natrium reactor. Natrium is the Latin and German name of the chemical element Na that's called sodium in English, which is why, confusing absolutely no one, the key element of the Natrium plant is a sodium-cooled fast reactor combined with an energy storage system. That it's a fast reactor doesn't mean it runs across Wyoming. It means it uses fast neutrons. Fast reactors use fuel that's more enriched in radioactive compounds. They can also recycle nuclear waste, in particular plutonium. That it's sodium-cooled means what you think it does. The energy that's created in the nuclear reaction is carried away by the sodium and then used to generate electricity. This also cools the reactor. One uses sodium because that has a high boiling point and can transport a lot of heat. It has the additional benefit that it doesn't catch too many of the fast neutrons because that could impede the reaction. Sodium-cooled fast reactors have been around for a while. The new thing about this one is that it comes with a built-in energy storage. You see, rather than creating energy from the hot sodium directly, they can transfer the heat from the sodium to a molten chloride salt and store that in a big tank. Then they can create the electricity later from that hot molten salt. This does, of course, reduce the efficiency because some energy gets lost in the conversion and storage, but hot molten salt has a very high storage capacity. The heat loss can be as low as a few % per day. And it has the added benefit that this nuclear power plant can effectively ramp up and down the electricity output very quickly. Now, contrary to myth, conventional nuclear power plants can ramp up and down, but they weren't designed to do it, and so it's not very efficient. Most of the currently operating nuclear power plants are what's called a pressurized water reactor. You can slow their nuclear reaction by putting boric acid into the water. This takes up some of the neutrons, so that creates less energy per time. A nuclear chill pill, so to speak. Newer types of nuclear fission reactors have control rods that can block some neutrons and slow down the chain reaction. That way you can ramp down nuclear power plants to 50% or so by something like 5% per minute, optimistically. It's not great, not only because that's not an efficient use of the fuel, but also because the temperature changes cause contraction and expansion, and not all components do that the same way, which creates stress on the material and so on. So while it's incorrect to say that nuclear power plants can't be ramped down, it's correct to say that they're not good at it. Kind of like Windows gets slower booting up every time you use it. So I assume Gates is familiar with the problem. Gas power plants, in contrast, can be ramped up and down very quickly, by 15 or even 20% per minute, just by adjusting the amount of gas burned. The new reactor in Wyoming gets around this problem by not ramping up and down the reactor itself, but by not always converting the energy directly into electricity. If the grid doesn't need the electricity, they park the reactor output as thermal energy in this molten salt. This means that such a reactor can even out grid fluctuations caused by fluctuations in wind and solar. This will work on the scale of hours or maybe even days, but the storage isn't efficient enough to make sense for longer periods. One thing one could do for longer storage is to produce hydrogen and store that. This will reduce the efficiency even more, but I guess better electricity produced with low efficiency than none at all. The new plant in Wyoming is designed to generate 345 megawatts and, if all goes according to plan, should begin operation by 2030. If successful, the project could position Natrium technology as a cornerstone in future energy infrastructure. A future that Germany will miss out on. But hey, who needs reliable power when you have lederhosen and beer? Can you really send a particle into the past? Someone asked me this last week because New Scientist published an article about this. You all know that I'm fond of retrocausality and would really like to go back in time to warn myself about this YouTube thing, so I've had a look. So can you send a particle into the past? The answer is that that's a completely meaningless statement. Particles don't go into the past or into the future. Particles are simply at some position at some time, or if it's a quantum particle, then they're at several positions. You see, a particle that goes left forward in time is the same as a particle that goes right back in time. Forward, backward doesn't mean anything. Unless you're a philosopher, then it means everything and also nothing at the same time. Schrödinger's meaning, if you will. Somewhat more technically, if you draw the curve of a particle into a space-time diagram, then that doesn't have a direction. You can really only talk about things going forward or backward in time if you have something that tells you which direction is forward, for example, from entropy increase. If you see water drops lifting up from puddles and disappearing into clouds, you could say, well, they seem to be going back in time. But a single particle doesn't tell you anything about it. It's just a particle. It doesn't know the difference between yesterday's burrito and tomorrow's existential crisis. Okay, so I hope that explains why the headline is nonsense. But that doesn't mean that the paper is nonsense. So let's look at what they did with the particles that supposedly went back in time. The paper in question is a general idea laid out last year with an experimental confirmation that just recently appeared on the archive. The general idea is this. You create an entangled state of two qubits. That they're entangled means that they're correlated in some property, but you don't know the value of the property for each individual particle. A typical example is spin. Think of it as an arrow that points into a specific direction. Let's say the spins are correlated in that they point in the exact same direction, but you don't know which direction this is. If you believe in the standard interpretation of quantum mechanics, then you'd say actually this spin doesn't have a direction until you measure it. The situation they look at is that you want to make a very precise measurement of some property of a quantum system. That could be, for example, some property of a material, magnetic field or such. You do this by bringing a quantum particle in the vicinity and then measuring how the quantum particle's spin changes. It's kind of like sniffing a t-shirt to see if it needs changing. To get any useful results, you need to repeat this many times. So it's a long sequence of particles going by the sample. However, the issue is that this measurement works best for certain values of the spin, and you don't know this spin, so some of your measurement results are not very good. So what can you do? What you can do is to create a pair of entangled particles and send one past the probe. Then you first make a measurement on the one particle to figure out whether it was a good probe. If the first measurement says it wasn't a good probe, you throw the other particle away. If not, you measure it. This way you can improve the accuracy of the measurement. And they say it's something to do with going back in time, because after you've made the first measurement on the one particle, it's like you retroactively select the spin at the time it was created. Because remember, in quantum mechanics, the idea is that the spin didn't actually have any value until you measured it. This idea is known as post-selection. You select certain quantum particles after you produced many more. Does this really have something to do with going back in time? I'd argue no. Let me give you an example that's a little easier to digest than spins and probes and entanglement. Suppose you post a comment on X Twitter and get a lot of replies, some agreeing with you, some disagreeing. You then go and block everyone who disagrees with you and hide their comments, like certain climate scientists are known to handle such things. But I digress. If you look at your post and the comments afterwards, it's like you went into the past and magically made those critics disappear. This is what post-selection means. Does this mean the comments you removed never happened? I regret to inform you that they still happened because you know what, you can't change the past. And it's the same with these post-selected states. Just because you decided to throw away some states doesn't mean you changed the past. That said, this doesn't mean it's a useless idea, because this procedure has a practical advantage, and this is really what the paper's about. You see, by selecting only the best probes, you reduce the frequency with which you need to make a measurement to reach a certain accuracy. That's useful because a lot of detectors have a dead time after detection. Basically, after you make a measurement, there's a certain period in which you can't measure anything else. It's like a stand-up comedian who delivers their jokes too quickly. You just can't laugh that much. You need a break in between. Same with these detectors. And if you select only the good probes, that gives the detectors breaks. So this idea is actually useful and has some practical purposes. But no, they're not actually sending particles into the past, because if they could do that, they wouldn't be writing papers about it, they'd be trading big. A group of physicists want to use artificial intelligence to prove that reality doesn't exist. I wish this was a joke, but I'm afraid it's not. It's actually worse. They don't just want to use AI, but also quantum computers. The worst part is that I think they're serious. This one's a little tough to explain. Let's start at the beginning. Or is it the end? Who knows in a reality that doesn't exist? The new paper is a follow-up on an idea that made headlines 2 years ago as a supposed proof that reality doesn't exist. You'd think that if your theory implies that reality doesn't exist, then maybe, just maybe, there's something wrong with your theory and not with reality. But this is how normal people think, not how physicists think. Physicists think this needs to be taken seriously. I made a video back then explaining this mess, but I know you don't want to go and watch the whole thing, so here's a brief summary. In the most common interpretation of quantum mechanics, the outcome of a measurement is not determined. The theory merely makes probabilistic predictions, and it's only once you make a measurement that the outcome actually has a specific value. Unfortunately, quantum mechanics doesn't tell you exactly what a measurement is. That's part of what's called the measurement problem, and it's the origin of the idea that reality doesn't exist. The reasonable take on the measurement problem is that there is some good definition for what a measurement is. We just don't know it yet. A measurement is the interaction with a device called the detector. And even though we can't formally write down exactly what a detector is, we know what they do. They make measurements. That's the reasonable take. But the vast majority of physicists do not agree on this. They believe that a measurement is not a physical process. This causes the following problem, first pointed out by Eugen Wigner, known as Wigner's friend. Imagine you're Eugen Wigner. Though he's been dead for 30 years, so maybe don't. Imagine you're the reincarnation of Eugen Wigner. Your friend is in a lab working with a quantum particle that could appear either left or right on the screen. Before you measure the particle, it is, as we say, in a superposition of left and right. But once your friend measures the particle, she'll find it either left or right, not both. It's like Schrödinger's cat, but with less fur and more lab coats. Let's say she finds it left. You knock at the door and ask what she measured, and she says, well, it was left. So far, so obvious. But if you think the measurement is not a physical process, then you'd say the measurement only happens once she tells you the outcome. And before that, your friend herself was in a superposition, one in which she measured the particle left and right at the same time. And it's only once she tells you the result that the superposition of her disappears. Physicists have discussed this story of Wigner's friend for like half a century. Then in 2016, they made it more complicated by saying you could use two people in two laboratories with two friends and two particles that are entangled. That's what they call progress in physics nowadays, making insane ideas even more insane. Then in 2018, Czeslaw Bruckner proved that if these two people in the laboratories could be in superpositions, which of course they cannot, then all four people can't agree on the outcome of all experiments. And this is where the headlines come from, that reality doesn't exist. Because if you buy that people can be in superpositions, then you have to conclude that there is no external world that's independent of us. It depends on where we are and who we talk to. In 2019, then, a group from Edinburgh made an experimental test that tested the predictions for this extended weakness friend scenario, except that they replaced the friends with photons. Now, you might argue that photons aren't people, and you'd be right, and that finally brings me to the new paper. The authors argue that they can circumvent this photon problem by taking an artificial intelligence that plays the role of the friends in the two laboratories. They say it has to be sufficiently intelligent to plausibly make an observation, so they assume human-level artificial intelligence. Then they say we will put this AI on a quantum computer, and since it's a quantum computer, so the observer can indeed exist in a superposition. There are two minor problems with the idea. One is that we don't have human-level artificial intelligence. And the other one is that we don't have quantum computers remotely large enough to run any AI on them. But the much bigger problem is it doesn't make any sense. First, you don't need intelligence to make a measurement. You just need a detector. Though, what do I know? If you think your friends are photons, then maybe you also think fluorescent screens are intelligent. And second, if whatever it is that you use to make the measurement doesn't collapse the superposition, then it wasn't a measurement. You can't have your cake and eat it too. Just in case you're still imagining your weakness reincarnation and talking to photons had you missing the more subtle nuances, I think this is nonsense. So why am I telling you this? It's because it highlights a very important point. It's that the larger the quantum systems that we can create, the better we can test which type of configuration does and doesn't destroy superpositions. This means that there have to be certain configurations that you can put on a quantum computer which you can't put into a superposition any more than dead and alive cats. And if we figure out just which ones those are, we'll have solved the measurement problem. Oh dear. Can you have an existential crisis if reality doesn't exist? Let me know in the comments. Physicists from the University of Queensland in Australia have found evidence that time ran slower in the past. This may sound like they climbed into the attic and excavated a dial-up modem, but it's actually to do with supernovae. Let's have a look. This video comes with a quiz that lets you check how much you remember. You've probably heard of cosmological redshift, which means that light from faraway galaxies is shifted to the red as it travels towards us. This happens because the universe expands as the light travels, and that stretches the wavelength of the light, so it becomes more red. This cosmological redshift is how we know that the expansion of the universe is actually speeding up. A Nobel Prize was awarded for this in 2011. You've probably heard of this, but what's far less well known is that shifting light to the red is not the only thing the expansion of the universe does. Another effect is that when we look back in time, everything seems to happen slower. It's called time dilation in general, or cosmological time dilation in this particular case. Indeed, the two things, redshift and time dilation, necessarily go together. Think about it this way. If you have a wave, you could use each crest of the wave as a tick of a clock. Now, if the wave shifts to the red, it stretches and those time markers move apart. It's a direct consequence of Einstein's theory of general relativity. And yes, this time dilation is the same effect that slows down time near a black hole. You see, if you're near a black hole and you want to send a signal to someone far away, then the signal needs to escape. So it has to work against the pull of gravity. But it can't slow down because light always moves with well, the speed of light. So rather than slowing down, the light instead loses energy. And that means that its frequency becomes smaller and the wavelength longer. It gets redshifted. The closer to the horizon you are when you send the signal, the more it gets redshifted. But as we just discussed, you can think of the crests of the wave like ticks of a clock. So this also means that the duration between the ticks becomes longer. Indeed, if you send a signal from the horizon exactly, it can't escape at all. This means if someone is falling into a black hole, for the faraway observer, it seems like their image gets increasingly redder and is moving slower and slower. It's like watching paint dry, but in space. It's a fascinating consequence of Einstein's theory. Unfortunately, it's very hard to test nearby black holes because we don't have reliable clocks there. But you can test the same effect, the relation between redshift and time dilation, by looking back in time, and that's what they did in the new paper. In this paper, a group of astrophysicists reports that they've seen a systematic slowdown in supernovae explosions. You see, a supernova emits a lot of light at many different wavelengths. The further away it happens, the redder the light looks. You see this illustrated in this image where the black curve is the emission from the supernovae that shifts towards longer wavelengths. This is the redshift. But it should also just take longer for these explosions to fade away the further away they are. That is, the redder the supernova, the longer it should last. Specific types of supernovae, known as type 1a, fade in a very regular way, and so you can use them to find out how much time slowed down by checking if there's a correlation between the redshift and the duration. That's what they looked for in data from the dark energy survey collected at the Cerro Tololo Observatory in Chile. And the results agree with Einstein's theory. But what does it mean that time ran slower in the past? If someone was alive back then, would they have noticed any difference? No, they wouldn't, because everything happened slower back then. So they wouldn't have been able to tell. It's just in comparison to today that we see a difference. This is also why the observer who falls into a black hole themselves doesn't notice any slowdown. They just fall in and cross the horizon, and that's that. It's just the distant observer who sees them slowing down. And it's not that they stop falling before they reach the horizon. They really do fall in. It's just that on the outside you can't see it. Though, to be precise, since black holes evaporate, we would eventually see it, but it'd take 10 to the 100 years or so, just enough time for the US election campaign to finish. There are two ways to look at this result. One is, Einstein was right again. How boring. The other is that this is the reason why Einstein's theory is so difficult to improve on, because it has so much evidence speaking for it. Unless, of course, you believe that the Earth is flat, in which case I guess time dilation is just a hoax that physicists have invented to sound smart, which really explains a lot, doesn't it? Thanks for watching. See you tomorrow.